Welcome to Math 2320. This is section 8.2. We're looking at solving a system of differential equations using matrices, eigenvectors, and eigenvalues. What does all that mean? So I'm going to form matrix A based on the coefficients 4, 5, 10, and 9. I calculate the determinant of A minus lambda I, where I is the identity matrix. So it's essentially 4 minus lambda, 9 minus lambda on the diagonals. The 10 and the 5 stay there. So to form this determinant, it's a downward diagonal minus the upward diagonal. And so continuing that and grinding this out, I got 4 times 9, 4 times minus lambda times 9, and a lambda squared. So clean all this up, minus 50. You set this equal to 0, and this is called the characteristic polynomial. It is factorable, and when you solve it, you get the eigenvalues. And the eigenvalues are 14 and minus 1. With each eigenvalue, you get one or more eigenvectors. Alright, so using my first eigenvalue of 14, I solve A minus 14i times some x is 0. Alright, so when you take A and you subtract 14 down the diagonals, you get this particular matrix. And then if you add the two equations together, the second row is all zeros. And so what you see by that is x2 is free, x1 is 1/2 x2. So if you write that in the vector format, you get x2 times 1/2 and 1. But to make the calculations easier, you multiply through by 2, and so your eigenvector that goes with 14 looks like that. You repeat the process for the eigenvalue of minus 1. So that's really just A plus I. So you're adding ones to each of the diagonal elements. So when you clean that up, which is pretty easy, you multiply through by minus 2 and add. And so I get 1, 1, 0 and all zeros, which says that the x2 variable is free, x1 is minus x2. So rewriting that, that's x2 times minus 1, 1, giving me this eigenvector. What does all that mean? Alright, well, what it means is the following. For the eigenvalue of 14, the eigenvector that went with that is 1, 2, and you pick up a C1 if we had initial conditions. For the eigenvalue of minus 1, I get an e to the minus t with its eigenvector of minus 1 and 1. Alright, so in question 2, we repeat the same process trying to solve this particular system. So I form the determinant of A minus lambda I. Alright, and so it's just 8 minus lambda minus 12 minus lambda and 8 and minus 8. Multiplying down the diagonals, I get 8 times minus 12, I get 8 times a minus lambda. I've got a minus lambda times a minus 12 and a lambda squared. And this minus a minus 64 is a plus 64, giving me the characteristic polynomial. All right. And so this is factorable as lambda plus 8, lambda minus 4. All right, and so my two eigenvalues are minus 8 and 4. Solving for the eigenvector that goes with minus 8, it's a plus 8ix. All right, so putting that in, I've got to figure out when is this 0. So I switched row 2 to be row 1, multiplied through by minus 2 and added it to get all zeros for row 2. So that tells me x2 is free. x1, which I would get from this row, is simply 1/2 x2. So that gives me here a basis for this eigenspace, for this eigenvalue, and so it's 1/2 1. But to make life easy without fractions, multiply by 2, and I get 1, 2. I repeat the process for the eigenvalue of 4. All right, so do that. Solving this, I can divide this row by 4. I get 1 minus 2, 0. And if I multiply this row by minus 8 and add, I get a row of all zeros. And so that tells me then that x2 is free again. I get x2 is free, so x2 multiplied by this, so this is times, and I get for here a 2. And so for the eigenvalue of minus 8, its vector was 1, 2. For the eigenvalue of 4, I get the eigenvector of 2, 1. With the constants C1 and C2 to be determined if we had initial conditions. All right, in question 3, we have 3 equations. All right, so we form the matrix and get the determinant of A minus lambda I. So each of the diagonal elements minus lambda. All right, so I need to do this 3 by 3 determinant. I can expand by any row or column. I'm going to go ahead and expand by row 1. So it's my first element times this cofactor in here. All right, this sub 2 by 2 determinant. And then because of this position, it's a minus 1. And times this subdeterminant. Now it's just a question of keeping track of everything. It's this one times the downward diagonal, minus 7, and then minus 1 times this diagonal, minus 0. All right, so cleaning this up a little bit, we get the inside part here. All right, distributing the minus 1 here. All right, and at that point we've got this fairly cleaned up, and so I'm to here. Now I don't really want to multiply this out, and so what I'm noticing is the following. I can factor a minus 1 out of this first piece, and then this piece is in common to both terms, so factor it out. And then I'm left with what? Well, I'm left with minus 1 times that piece plus the 1 that's sitting in the front there. Cleaning that up, all right, and now I'm going to take the minus 1 back out because I don't really need it. All I need are these pieces. And so this piece is factorable, and I get eigenvalues of minus 1, 7, and minus 2. Alright, so with the eigenvalue of minus 1, I have to solve this problem to figure out the eigenvector that goes with that. Alright, so it's fairly straightforward. I get x3 is free, x2 is 0, and x1 is minus x3. And so I get minus 1, 0, 1. Repeat the process for the eigenvalue of 7. And again, just grinding it out, do row operations to clean this up a little bit. Pretty quickly we get a row of all zeros. And so I get x3 is free, meaning free to pick whatever I like. And so I can write it as x3 times 1, 8 sevenths, and a 1 seventh. And again, to get rid of the fractions, multiply through by 7, and I get 1, 8, and 7. Again, I repeat this for lambda equals minus 2. Same process, plug it in, solve with row operations, and I get x3 times 1 seventh minus 1 seventh and 1. Clearing the fractions, multiplying by 7, we get to there. Long and tedious, yes. Easy to make mistakes, yes. So be careful not to make some silly adding mistake, multiplying, or just miscopying. And so we get for each of the eigenvalues the corresponding eigenvector that goes with it, C1, C2, and C3. In question 4, we have a practical problem. We have pure water coming in to some tanks, different size tanks, A, B, and C. We want to solve this for different initial conditions. All right, now there is a solution. They gave us a solution, so let's just step through that. So here's our problem. You form A minus lambda I. All right, so that's just minus lambda on each of the diagonals. Now to get the eigenvalues, I simply need to find the determinant. Well, the determinant of this is fairly easy because I can expand by the first row and I only have this one element. So it's that element, this one, times this smaller 2 by 2 determinant. But the upward diagonal of it is 0. So essentially I already have my product. And so that's how they got these 3 eigenvalues. You can do exactly what we did before to figure out k1, k2, and k3. Those are just the eigenvectors that correspond to that eigenvalue. Alright, and so now if you plug in your initial conditions, what those were, you can solve for C1, C2, and C3. And so you get solutions for x1, x2, and x3. But what you can notice is as time goes to infinity, these are all negative exponentials, so they are decaying to 0. So what they're saying is eventually all the tanks will contain pure water. because if you remember, we had pure water entering the tank. In our last problem, looks fairly simple, but turns out to be a bit of a problem. Alright, it's just a 2 by 2, so I try to form the determinant a minus lambda I. So here's my determinant equals to 0. Downward diagonal minus this minus 4. And so what I end up with is this characteristic polynomial. I see that I've got a repeated root, and so that says lambda is 4. Now that by itself is not bad. If we can get two eigenvectors that would go to that eigenvalue. Well, let's see. Putting in that eigenvalue, I form a minus 4i. Now I'm going to solve when is it equal to 0, which is very easy to solve. I get x2 is free, x1 is 2x2. So I get my eigenvector is 2, 1. There's only one of them. I need two of them. So that's bad news, but if you looked in the textbook, we do get a second solution. And the second solution is going to be of the format KT. If you remember it a long time ago when we had something with repeated roots, we introduced a t into the process. So the x2 is kt e to the lambda 1t, my first lambda, which is 4, plus p e to the lambda 1t. The k we speak of is the eigenvector that we already have. P1 and P2, we need to figure out what that is. So we have to solve a minus our repeated lambda I. I need to solve for p equal to k. What k? My eigenvector. Alright, so that means I need to solve this question. Alright, which is not too difficult to solve. I get a row of zeros fairly quickly, and so I get P2 is free and P1 is minus 1 plus 2P2. So to make life easy, I just pick P2 to be 1, and if P2 is 1, I get 2 minus 1 is 1. So my P vector is 1, 1. So putting that together, x1 from my first solution looks like this. My second one has our kt e to the 4t and p times e to the 4t. So now my initial conditions were minus 1 and 7. So what does that mean? Well, if I plug in t is 0, I get e to the 0 is just 1, so I get 2, 1 and c1. And what about c2? Well, if t is 0, that term is gone, and I get 1, 1. So now I have to stop and figure out, well, what is c1 and c2? So I get 2, 1 minus 1 and 1, 1, 7. So I switched row 2 to the top so I could use the 1. I got rid of the 2. Divide by minus 1 and now make a 0 above it. And so what that tells me is C1 is minus 8, C2 is 15. Alright, well let's see, 15 times 2 is 30, 15 times 1 is 15, so that's for the t e to the 4t. For the e to the 4t, I've got two pieces, this piece and the second. So let's see, minus 8 times 2 is a minus 16. Minus 16 plus this 15, I get a minus 1. I get a minus 8 and a 15, so a positive 7. And so we finally have our solution, even though we had a repeated eigenvalue which only had one eigenvector.